So, as the title suggests, today's session is about autonomous systems. When you hear about robotics, you may first think of robot manipulators and mobile robots in the factories. But robotics has grown beyond that. And autonomy is a trend happening across industries. You will find defense contractors building next generation autonomous underwater vehicles, autonomous drones, unmanned ground vehicles, and autonomous vessels. You can also find traditional big machine makers in the construction, mining, and agriculture actively investing in autonomous capabilities. And in the advanced air mobility trend, there are also commercial aircraft makers adopting similar sensing and automation technologies from robotics into their aircrafts. Today's webinar is the second webinar in the series about autonomous system. The first webinar was held on 17th September, and in that we have covered model-based system engineering for autonomous system design from architecture to implementation, followed by verification and validation. So, in that webinar, we have explained about the different MathWorks tools that can be used for those activities. Today's webinar is more focused on the system design and dynamics modeling, and we will also give an overview about the software in loop, processor in loop, and hardware in the loop testing as well. So here is the agenda of the webinar. First, we'll have a look at different phases of the autonomous system development where the MATLAB and Simulink tools can be used and highlight the focus of the webinar series on autonomous systems. Secondly, we will consider common questions from robotic engineers. Next is system design and dynamics modeling for autonomous systems and what all MathWorks tools are available for the same. It is followed by an overview on different testing methods like software in the loop, processor in the loop, hardware in the loop with Simulink real time and Simulink test. I'll also explain different MathWorks support mechanisms. Okay, so as I mentioned, we were conducting a series of webinars on autonomous systems. The webinar one was focused on a model-based system engineering for autonomous system from architecture to implementation, verification, and validation. In webinar two, that means today's webinar, we will be talking about the platform design and also we will cover a part of the verification and validation. Mainly the SIL, PIL, HIL methods. And there is an upcoming webinar also, the date for which will be announced through CES website, the LinkedIn pages, etc. So in that webinar, we will be covering more towards the autonomy algorithms, which is used for localization, planning, sensor fusion, and control. And we will also cover the hardware deployment as well in the next webinar. So let's start with the common questions from the robotic engineers. So I have listed something there like, how do you model the sensors and platforms, mainly the robot models you need to model, and then the sensors needs to be modeled. And when it comes to the autonomous algorithms part, okay, how can we design the algorithms for perception? How do you do the planning algorithms? How can we control it? And when it comes to the hardware part, how do you test and deploy the robotic applications? How can we simulate? How can we analyze it? How can we deploy the algorithms? How can we generate the code for these algorithms? And how can we deploy it to the algorithms? So in this, throughout this webinar, we will mainly consider how can we model the robot models, how can we model the sensor models, and as we have included an overview of SIL, PIL, HIL, we will be focusing a little bit on the right hand side also, like the testing and the deployment. Okay, let's go to system design and dynamics modeling part. As you know, autonomous system domain is very vast and it is impossible to discuss the platform design of all verticals. So what I have decided is we will be taking examples of platform development for UAV, AUV or mobile robot, but we will share the details of MathWorks solutions which can be used for autonomous systems in general. Okay, so I have shown this slide before. Let's start with the modeling of the robots. So how do you model the robots and the sensors? So when it comes to the modeling, it can be a physical model, or it can be a kinematics model, or it can be an external model. If it is a physical model, let's consider the example of a bumper car. Okay, before going into the example, let me add one point here. All the examples used in this webinar are available in MathWorks website. You can either use the same text for finding it from the MathWorks website, or you can, if you face any difficulty in finding these examples or any resources which we are mentioning here in the webinar, you can reach out to us. Okay, so this webinar, this example, it's about a bumper car. It basically shows a toy bumper car traveling down a series of ramps while undergoing intermittent collisions. So mainly the tool used here is Simscape multibody, and block which is used in this example is a spatial contact force blocks. It can be used for modeling the friction and normal forces between every pair of geometries that may potentially come into the contact during the simulation. And when it comes to kinematics model, this is an example of simulating different kind of kinematics model for mobile robots. This is available with the robotic system toolbox. Okay, so basically there are a number of ways to model the kinematics of mobile robots. This example shown here, it basically shows how to model different robot kinematics models in an environment and compare them. And uh, we have MATLAB supports kinematics modeling from the simplest unicycle kinematic model to differential drive kinematic model, bicycle kinematic model, a Kerman kinematic model, etc. And on the right hand side, it is an example of an external model. Like, you have the model developed in an external software like a Gazebo. So you can co-simulate the Gazebo with Simulink. So this particular example shows how to control a differential drive robot in Gazebo co-simulation using Simulink. The robot follows a set of waypoints by reading the pose and wheel encoder positions and generate torque control commands to drive it. It uses robotics system toolbox and Simulink mainly. All right. Coming into the modeling of robotic dynamics, again, the main tool which we suggest here is Simscape multibody. So it supports the dynamics modeling for automotive, two-wheeled vehicle, crawler, legged, and drones. It comes with the contact forces library, and it also supports CAD import from third-party tools. We'll see more details of the capabilities of Simscape multibody in upcoming slides. And when it comes to modeling of the underground vehicles or heavy vehicles, again, we have different criteria, like whether it is a physical modeling or a vehicle model, or it's just the vehicle dynamics. Again, we have the Simscape multibody being used there, and we also have for modeling the vehicle dynamics, we have the vehicle dynamics block set. Okay, so in the first example, it basically shows a scissor lift model with hydraulic actuation built using Simscape multibody and Simscape fluids. So this scissor lift model is assembled from a library of parameterized component models. And in the second example, it basically uses the virtual vehicle composer app available with a vehicle dynamics block set to configure and build a virtual vehicle that can be used for system level performance analysis, which includes ride and handling evaluation, chassis controls development, software integration testing, and hardware in the loop testing. It supports vehicles, motorcycles, and trailers with the 1D OF, 3D OF, and 6D OF motion. And on the right side, these are the options available, few options available in vehicle dynamics block set. It basically provides fully assembled reference applications of vehicle models running driving maneuvers in 3D environment. that is integrated with Simulink. You can create your own versions of the reference applications, providing a framework to test that your vehicle meets the design requirement under normal and extreme driving conditions. This is an example of modeling and control of a Mars rover. So this one shows the steps included in that. So it includes the Mars rover modeling, then terrain modeling, spatial contact force modeling, path tracking control, and end effector control. So the grid surface block is what has been used for modeling the rigid terrain surface. Mainly the tools used for this example are Simscape Multibody and Robotic System Toolbox. And point cloud and spatial contact force blocks are used for modeling the contact between the rover wheels and the rigid terrain. Pure pursuit is used for path tracking control of the rover, and kinematic solver and trapezoidal velocity profile trajectory for joint space trajectory planning and control of the rover arm. And you can find this example also in MathWorks website. We'll see the details of it in later slides. Next is about the sensor models. How can we import the sensor data? How can we simulate the sensor models? If it is an external sensor model, how to work with that? So these examples, the first one is about importing sensor data. It uses the read data block to play back the data from Rosbach log file recorded from a Jackal robot from ClearPath Robotics. And this example uses ROS toolbox and Simulink. And in the next example, it's about how to model IMU, GPS, INS, and GPS. Okay, so it basically it is done with the help of navigation toolbox. It helps you to model inertial measurement units, global positioning systems, inertial navigation system, etc. So you can actually model the specific hardware by setting up the properties of your models to values from hardware datasheets, and then you can tune the environmental and noise properties to mimic the real world environments. You can use these models to test and validate your fusion algorithms or as placeholders while developing larger applications. So you can search with the same text in the MathWorks website to find this is basically a tutorial, and it provides an overview of inertial sensor and GPS models in navigation toolbox. Next one is about the external model. So here it's about the co-simulation between Simulink and Gazebo. This example mainly uses robotic system toolbox and Simulink, and it basically explains how to set up a synchronized simulation between Simulink and Gazebo to send commands and receive data from Gazebo. We have more examples, and this will help you to find errors in wheel encoder. And if you want to create synthetic sensor data, how to do that? So the example in the middle, it will help you to create synthetic sensor data from inertial sensor. And on the right side, it's about automatic tuning of the INS filter. INS filter, async filter. So it's basically an object and it's a complex extended Kalman filter that estimates the device pose. But manual tuning of this filter or finding the optimal values of the noise parameters can be a challenging task. This example illustrates on how to use the tune function to optimize the filter noise parameters. And if you have any questions, please feel free to post it in the chat window. The CES team is here to support you on that. And this slide is about perturbing IMU sensor readings. Perturbations are essentially the errors on the individual measurements. Examples of such perturbations include uncalibrated sensors. So in the navigation toolbox, we have perturbations and perturb functions to perturb the IMU sensor readings generated by IMU sensor system object. By doing perturbing the IMU, you can perform the noise analysis to test your fusion filter with the different IMU parameters and noise ranges. So first, for that, you need to create the IMU sensor object. Then you have to show the perturbable properties and then apply it and simulate the IMU sensor data with the perturbations. And this is about how to generate off-centered IMU readings. So this example basically it generates two 9-axis IMU readings, one IMU mounted at the vehicle's origin and the other one mounted at the driver's seat. So you can specify the offset between the vehicle origin and the IMU mounted at the driver's seat, and you can also visualize the locations of the sensor. It basically uses a navigation toolbox. And the next one topic in the sensor modeling is about how to do the LiDAR and camera calibration, how to do the multi-LiDAR calibration, how to work with the Velodyne LiDAR, etc. So the example on the left-hand side, it uses the LiDAR toolbox, Simulink, and automated driving toolbox. The use of the multiple LiDAR sensors on an autonomous vehicle helps to remove the blind spots, increase the redundancy, enables high resolution map creation, etc. But to extract meaningful information from multiple LiDAR sensors, you can fuse the data using transformation between them. Fusing multiple LiDARs can be challenging because of the variations in resolution between different LiDAR sensors. This example basically demonstrates on how to create a high resolution point cloud map by fusing the point clouds from multiple LiDAR sensors. And in the second example, it basically shows how to handle the Velodyne scan messages from Velodyne LiDAR. This Velodyne ROS messages store data in a format that requires some interpretations before it can be used for further processing. MATLAB can help you by formatting the Velodyne ROS messages for easy use. And on the right hand side, this example help you with the LiDAR and camera calibration. So basically it consists of converting the data from a LiDAR sensor and a camera into same coordinate system. It enables you to fuse the data from both sensors and accurately identify the objects in the scene. So this calibration establish correspondence between 3D LiDAR points and 2D camera data to fuse the LiDAR and camera outputs together. And so we have discussed about what are the options in MathWorks for the robots modeling as well as the sensor modeling. So this is an example of a UAV package delivery. It basically shows through the incremental design iterations. It basically shows through incremental design iterations, learn how to implement a small multi-copter simulation to take off, fly, and land at a different location in a city environment. And this example uses UAV toolbox, aerospace block set, aerospace toolbox, control system toolbox, navigation toolbox, state flow, Simulink, and Simulink 3D animation. And in this example, the steps involved are: first we have to set up the model for a four waypoint mission using low fidelity multi-rotor plant model. Then we have to connect it to, once the model is set up, we have to connect it to a GCS. Okay, and then we can set it in a basic cuboid scenario, and then if you have the obstacle avoidance algorithms to be incorporated into this one, we can do that. And then the same can be tested in a photorealistic simulation using Simulink 3D animations. So the end result is what you are seeing here. We'll see the details of this model in the upcoming slides. So I mentioned the previous one was about how to develop a UAV model in an iterative way. So and today's webinar focus is on the system design. So we will just see how to do the plan model in an iterative way. So before designing a flight controller, a model of the plant is anyways needed, right? So I mentioned Simulink, UAV toolbox, aerospace block set, and Simscape can provide the tools for that. And we can develop a UAV model from a low fidelity to high fidelity in 3 different stages. So what is the advantage of developing the plant model in Simulink? So what you get here is you have the freedom to decide on the appropriate level of fidelity. You can start with one of our approximate guidance models for low fidelity and build a more precise model using point mass and environment block provided in our tools, or use Simscape to build a high fidelity physical model of the plant. So the left hand side shows the low fidelity guidance model which is available in the UAV toolbox, and as more details are available, you can migrate it to the high fidelity model, or you can, if you have a specific design in mind, then you can use Simscape multibody to import the platform design into Simulink environment. This example covers the process of transitioning through these stages of fidelity. I'll play a video now. So this example is also available in MathWorks website. It explains how to transition from low fidelity to high fidelity. So UAV algorithm designer can start with a low fidelity model and evolve their planned model as and when additional data becomes available to concurrently design a guidance algorithm sooner. Designing a guidance algorithm using only low fidelity model can also pose risk. Without a controller or aerodynamic constraints, an optimistic guidance technique can fail for a real UAV with slower aircraft dynamics. So let's assume let's assume you have only the informations like roll, height, and airspeed shown in the table for the low fidelity modeling. So we can use the UAV guidance block, which is a reduced order model of the UAV. As you get more information like the lift and drag coefficients, and once you choose a motor for the aircraft, then you get the thrust curves also. Then we can go for the medium fidelity model, and you can test it. You can verify the medium fidelity step response, and also you can simulate the path following algorithms with the medium fidelity model. And once we get more information like all the forces, the moments, then we can use a high fidelity plant and input all the forces and moments to a 6DOF block, adds onboard sensors, model actuator dynamics for the UAV. This model basically reuses the outer loop controller designed for the medium fidelity model. And to validate that medium fidelity model provided and to validate that the medium fidelity model provided useful intermediate information, and then we can reuse that for the higher fidelity model also. And you can see here I mentioned all these examples are taken from the MathWorks website. You can use this copy command option and paste it in the MATLAB command window to rerun these models in your MATLAB. And this is an example of platform modeling of AUV. So basically, ocean engineers can use MATLAB and Simulink to build powerful yet efficient multi-domain models of underwater platforms. The model which is shown here, the platform is developed in SolidWorks, and the further physical modeling is done with Simscape and Simscape multibody. It allows the integration of hydrodynamics, fluid effects, dynamic behaviors, and inertial effects from the CAD models. And Simscape Electrical is also used here. It basically allows you to build models of electronic and mechatronic components like batteries, thrusters, and entire power systems. So combining domains into a realistic electromechanical plant model helps in the evaluation of system designs and performance, simulation of failures, and a variety of trade studies and autonomy algorithms. And you can, for more details, you can, for more information on modeling the autonomous underwater vehicle, please check the AUV tab under aerospace and defense page in solution sections in MathWorks website. All right, so I have just just try to touch all top level of robotic modeling as well as the sensor modeling, and we also consider the AUV platform modeling. So this table shows the list of MathWorks solutions for platform, sensor, and control design modeling of autonomous systems in general. As you know, the topic is very vast, and the products for each autonomous system project may be different. This list given here may not be complete, but still it gives you an overview. So we have I have been mentioning about the Simscape multibody, Simscape electrical, Simscape fluids, etc. So it basically helps you to model and simulate multi-domain physical systems. And we also have robotic system toolbox. It helps you to design, simulate, test, and deploy robotic applications. And we have the ROS toolbox, with which you can design, simulate, and deploy robotic operating systems based applications. And we have UAV toolbox. It provides tools and reference applications for designing, simulating, testing, and deploying drone, unmanned aerial vehicle, advanced air mobility applications. And we have aerospace toolbox. It helps you to analyze and visualize aerospace vehicle motion using reference standards and models. And there are few more toolboxes which is mentioned. It basically helps you with the sensor modeling. And we also have the vehicle dynamics toolbox. It provides pre-assembled automotive vehicle dynamics reference applications. And let's see some of the main toolboxes related to platform design. So first and foremost one is the Simscape multibody. It basically helps or it enables the multibody simulation of 3D mechanical system. With Simscape multibody, you can refine the requirements for the mechanical system. You can discover the integration issues early. You can design the control system, you can design control algorithms and logic. You can also test the embedded software without hardware prototypes. And if you find, if you face any difficulty while developing your application using the Simscape multibody, okay, I couldn't find the particular block from that. We also support importing designs from other CAD software. So you can assemble bodies and joints, including import from CAD softwares. So the key features are Simscape multibody support part definition tools. You can import parts and assemblies from CAD software. You can also use standard and custom kinematic relationship. You can also simulate models for dynamics and kinematics. And then it also supports for the C code generations. So you can test the embedded controllers without hardware prototypes. So let's have a look at the part definition features of the Simscape multibody. So as mentioned, it supports standard, custom, and CAD geometry. You can define frames in 3D interface, and the variable solids are other supported one. Flexible bodies are also supported. And coming into the CAD import, as mentioned, you can import either the part definitions or coming to importing of CAD assemblies, you can import the CAD assemblies from SolidWorks, Inventor, Onshape, or PTC Creo. And for the softwares like CATIA, NX, Solid Edge, CAD importing of CAD parts is what has been supported, and you have to use step files mode for that. I have more details in the next slide. So basically, Simscape multibody supports importing from CAD assemblies. So this can be supported with the Simscape multibody plugin. Okay, so there is an option. So Simlink plugin supported. If it is supported, then you can directly export from the CAD software in the form of XML files or stub files, and the full assembly can be exported to Simscape multibody. But for the CAD software which is not supported by Simlink plugin, then also you have options like you can use the native CAD and the step files, and you can refer the files directly. And coming into SimScape multi-body modeling environment, the constraints. So standard joints, gear constraints, custom constraints, cable mechanisms, and this is about the forces which can be modeled in SimScape multibody, general forces as well as the gravitational forces. When it comes to gravitational forces, it can be constant, time varying, or spatially varying. And for the visualization, you can review the animation, you can select the views, you can define the camera positions, you can explore the models, you can show or hide the objects, you can also export the video. So with SimScape multibody, you can test the embedded control system. So you have the physical system as well as the control algorithm for that. This control algorithm model. Sorry, here happened some technical issues. So with SimScape multibody, you can test the embedded control system. So you may have the control algorithm and the physical system. The control algorithm can be converted into C code or the CUDA code or HTML code, like in whatever format you want. It can be converted into that code format using the coders available from MathWorks. And this also enables HIL testing as well as the processor in the loop testing. All right, that's a lot of information about the SimScape multibody. But how can I miss mentioning about the SimScape vehicle templates? It's a set of templates for creating custom vehicle models using SimScape for use within the Simulink. With this, basically, you can explore the powertrain architectures for conventional, hybrid, or battery electric or fuel cell vehicles. You can also modify the suspension design by moving hard points obtained from CAD, and you can also connect the custom multi-link suspensions to hydraulic and pneumatic systems. Now you may think like, this sounds good, Anila, but this is not my cup of tea. Don't worry, we have more files for you. Just so you can see the name Steve Miller here, right? So I have placed a screenshot here. So if you just click on that, it will take you to this page, and there is a tab called File Exchange. So in this tab, you can see different Simulink multi-body files for example, robot arm with conveyor belts, running robot models in SimScape. You can see the model of industrial robot, and you can also see vehicle dynamics with the 14 degree of freedom. And you can also find the quadcopter drone model in SimScape. Mars, I have shown a Mars rover model in the initial slide, so this file can also be accessed from here. You can download it from this page. So it's available in MATLAB file exchange part. And another important toolbox in the field of autonomous system is the robotic system toolbox. It basically provides integrated environment for designing, simulating, testing, and deploying robotic applications. It also enables application deployment for manipulators, ground robots, and humanoid robots. So the robotic system comes with the robot models, specialized algorithms, simulation, and connectivity deployment. So in the robot models, you can model kinematics and dynamics of mobile robots and manipulators. It comes with a library of commonly used robots. It also has the provision to import URDF files or SimScape multibody models to create custom robot models. You can also visualize and simulate robot motion to validate your algorithms. You can also perform inverse kinematics calculation on your robot models. In the specialized algorithm part, For the manipulators, the toolbox includes algorithm for collision checking, path planning, trajectory generation, forward and inverse kinematics, and dynamics using rigid body tree representation. And for the mobile robots, it includes algorithms for mapping, localization, path planning, path following, and motion control. And to the scenarios and simulation part, you can author robot scenarios and incorporate sensor models to test the autonomous robot algorithms in simulated environment. You can also validate your robot models in Unreal Engine simulation environment or by interfacing with the Gazebo simulator. On the hardware connectivity and deployment part, you can connect with your robotic platforms such as Universal Robots UR or Kinova Gen 3 to deploy the cobot applications. You can also generate C or C++ code and the MEX functions for RCP, rapid control prototyping, or HIL, hardware in the loop testing. This toolbox also come with reference examples of pick and pick workflow and warehouse robots. You can access these examples from MathWorks website. And in 2024B, new manipulator and gripper models have been added to the robot model directory. The robotic EPIC cup vacuum assembly, EPIC 2 cup vacuum assembly, EPIC vacuum cup. These models are newly added in R 2024B. If you're working in this, using these models, don't forget to check it out. And ROS toolbox. It basically it is another important tool in the field of robotic application development or autonomous system development. So it basically provides an interface connecting MATLAB and Simulink with the robotic operating system. It can be ROS or ROS2. With this toolbox, you can design a network of ROS nodes and combine MATLAB or Simulink generated ROS nodes with your existing ROS network. It also enables you to verify the ROS nodes via desktop simulation, and you can desktop simulation and by connecting to external robotic simulators like Gazebo or to hardware. This toolbox also support in C++ and CUDA code generation. And you can also this also support for Simulink external mode. It basically helps you to view the messages and change parameter while your model is running on the hardware. Another important toolbox in the field of autonomous system is the aerospace toolbox. It provides standards based tools and functions for analyzing the motion, mission, environment of aerospace vehicles. It includes aerospace, math operations, coordinate system, and spatial transformation, and validated environment models for interpreting the flight data. It also includes 2D and 3D visualization tools, standard cockpit instruments for observing the vehicle motions. So we'll see in each in visualization what are the options available: environment models, vehicle motion analysis, satellite mission analysis. What all the options are available in the next slide. So in the visualization part, the aerospace toolbox include flight instruments, flight simulator interfaces, animation-based MATLAB, virtual reality animation, etc. And in the vehicle motion analysis part, we have the options for fixed-wing aircraft, flight parameters, flight instruments, data import, coordinate systems, unit conversions, etc. And for the control and stability analysis, fixed wing aircraft, flight control analysis, stability analysis, etc. are included. And for the environment models, I have listed few options there. And for the satellite mission analysis also, we have different options like constellations, eclipse analysis, orbit propagation, etc. Another important tool in the field of autonomous system is the UAV toolbox. It provides options for guidance, navigation, and control, scenario simulation, connectivity deployment, and HIL, and also flight data analysis. In the guidance, navigation, and control part, you have the UAV guidance models, waypoint and orbit follower, motion planning and path manager, controller templates, and PID auto tuning. And in the scenario simulation, we have multiple options like keyboard scenarios. It also comes with the UAV scenario designer app. And it also has wind and sensor models. It also supports constellation with the Unreal Engine. And when it comes to the connectivity and deployment part, it supports the Marveling protocol, and you can access the PX4 autopilot peripherals. Um, and it also supports in the controller deployment and hill testing with the Pixhawk and the QPilot hardware. We'll see a simple example of this part in the upcoming slide. And this toolbox comes with the 2 reference examples. These examples are available in MathWorks website. I have briefly explained the UAV package delivery example, and there is a VTOL controller template also available in MathWorks website. Another tool is the Simscape Driveline. It basically enables a physical modeling of multi-domain powertrain systems. With Simscape Driveline, you can refine the requirements for mechanical transmission systems. You can discover the integration issues early. You can design the control systems and logic within the Simulink environment. It is mainly intended for the rotational and translational systems. So these are some of the key features of Simscape Driveline. It comes with the gears, with meshing and viscous losses, clutch models, vehicle component models, translational components. You can also customize the components with Simscape language. It also supports in C code generation. Now let's move on to the second half of this webinar. It's overview of software in the loop, processor in the loop, and hardware in the loop. Although the title says about software in the loop and the processor in the loop, I prefer to start with the model in the loop, MIL. So here, as you can see this, you can see here that both the controller and the plant is in Simulink, right? So when we simulate it in this way, it's called model in the loop. Here both, as mentioned, here both controller and plant are simulatable models in the host PC. And when in software in the loop, basically in software in the loop simulation, it will generate the C code from the controller, and it will execute the code as a separate process on your host computer. So here what happens is, sorry. So from the controller, we can generate the equivalent code, and then this code will be executed in the same host PC, and you will have the plant model. So this code will be controlling the plant in software in the loop. But whereas in processor in the loop, we will here also we have to generate the code from the controller, but the code in this case will be running on the target platform. Target platform we want to test against. So in this example, you can see Raspberry Pi is the target platform. And in our hardware setup, the Raspberry Pi directly communicates with the, and the plant used here is Quanser Cube. So this the code will be flashed into the Raspberry Pi, and it will communicate with the plant here. Okay. But what is the benefits of doing this kind of test? Ultimately, we want to make sure that when we generate the code from the controller and the code performance is still acceptable. So by comparing the normal simulation results with the SIL or PIL results, you can test the numerical equivalence of your model and the generated code, and you can also make sure that you meet the real-time constraints. And this is the hardware in the loop testing. So what's the difference here? So here, the generated code is flashed into the microcontroller, but the plant model is in the target hardware. Okay, so it's not in the host PC anymore. In the previous SIL and HIL, the plant model was in the host PC, but for doing the HIL, you have to move the plant model to the real-time computer or the target hardware. So in HIL testing, controller model with the real production controller deployed on the target processor or microcontroller operates in the loop with a model of the plant running on the real-time target machine. In this configuration, you can test the production controller's response to fault conditions and potentially hazardous scenarios without the risk of associated with the such testing on the real plant. And Simulink real time and speed goat are the most recommended tools for this part. So it can basically take you from simulation to rapid control prototyping and hardware in the loop testing in a single click. You can create, control, and instrument real-time applications that run on the SpeedGoat real target computers directly from your Simulink models or with the MATLAB API or app designer. Basically, with the Simulink real test and Simulink real time and SpeedGoat, you can simulate and test control designs and dynamics of your robots and manipulators, autonomous system or motors or electric vehicles or powertrains or BMS, etc. This is an example. So here you can see both flight controller and plant models are there. So when we run it in this way, it is called model in the loop. Now, when we run the flight controller as a C++ executable using the autopilot's firmware on the host PC, this is what we call it as a software in the loop. And then when we deploy the flight controller to the autopilot hardware board, we basically have to call it as processor in the loop. But in some cases, like here you can see it's called as the hardware in the loop. But it's basically when you flash the code to the hardware, to the controller, flight controller, it is basically processor loop. In the next slide, you'll get more clarity on this. So this is just for the examples perspective, it has named as the named it as the hardware in the loop. You can also deploy the plan model on the hardware, and this is what we called as a full hardware in the loop workflow. So here the actuators, sensors, and other drone peripherals are also in the loop. As I mentioned before, when you flash, when you generate, when you use the generated code on the autopilot on the Pixhawk, it is nothing but processor in the loop. But when you the code is on the hardware or the auto Pixhawk, and when you keep the model, and I mean the plant model on the hardwares like the SpeedGoat, the target hardware, this is called a full hardware in the loop. I hope the point is clear. If you have any doubt, please feel free to post it in the chat. And we'll also have we mentioned about the software in the loop and the processor in the loop, and it needs the code to be generated, and we will be deploying that generated code on the microcontroller or on the related hardware. But how to generate the code for that? So MathWorks offers a range of coders for code generation. So we have the embedded coder for C and C++ code generation, HTL coder for VHTL and Verilog code generation, and we have the GPU coder for CUDA code generation, and this ROS toolbox in support with the MATLAB coder and Simulink coder. It helps you with the ROS and ROS2 node generation. And we also have the Simulink real-time as well as the SpeedGoat for helping you with the rapid control prototyping as well as hardware in the loop testing. These examples shows for AM, NVIDIA, GPU, and ROS node generation. In the first example, it basically shows how to generate code for an image segmentation application that uses deep learning. It uses the codegen command to generate a static library that performs prediction on a DAG network object for unit. And in the next example, it's basically for code generation for object detection by using single shot multi-box detector. This example uses GPU coder, deep learning toolbox, computer vision toolbox, GPU coder interface for deep learning. And the last one is how to generate a standalone ROS2 node from Simulink. It basically uses Simulink coder, and ROS toolbox. This example shows you how to generate and build a standalone ROS2 node from Simulink model. You can configure a model to generate C++ code for standalone ROS2 node. Then build and run the ROS2 node on your host computer. And these two are examples for generating code for the Raspberry Pi as well as the FPGA. And I mentioned about the software in the loop, processor in the loop, and hardware in the loop. So Simulink test is a MathWorks tool for doing all these things. It basically provides three main capabilities for testing models. You can there is a test manager, you can create the test harness, and you can also author the test. So with the test manager, you can author, manage, and organize the test. You can execute simulation and equivalence and baseline test. You can review and export the reports. The test harnesses helps you to isolate the component under test, and also it provides a synchronized and a simulation test environment. With the test authoring, you can specify the test inputs, expected outputs, and tolerances. You can also construct complex test sequences and assessments. Simulink real time. So Simulink real time and SpeedGuard take you from simulation to RCP or HIL in a single click. You can basically create control and instrument the real-time applications that you run on the SpeedGuard real-time target computers directly from your Simulink model or with the MATLAB API or app designer. So if you are interested to know more about the RCP, or if you are looking for solutions to do hardware in the loop testing, please contact CES. And this slide shows the overall products used in different phases of the UAV development. So in the first webinar, we discussed about system composer requirement toolbox and verification valid methods. Today's webinar was focused more on the platform design part. Okay, and we have also considered a few points. I have also discussed a few points about the coders and as well as the testing part, like PIL, HIL, and SIL. In general, for developing autonomous systems, model-based design is the recommended approach. So you can see here in different phases what all the tools are available. For the platform design, you can use MATLAB, Simulink, Simscape, Aerospace, Blockset, and Simscape multibody, and so on. And for the autonomous algorithms part, we have the sensor fusion and tracking toolbox, computer vision toolbox, robotic system, automated driving toolbox, navigation toolbox, reinforcement learning toolbox, etc. And for the deployment, we have different coders. And for the verification and validation, we have Simulink test, Simulink coverage, polyspace, and certification products like IEC certification kit. It supports in DO 178C and ISO 26262 certification, etc. And this slide shows not all the products are listed in this one, but again, model-based design is the recommended approach for autonomous system development. And here are some of the resources to help you get started with. So from the MathWorks website, you can access the ebook for developing the autonomous mobile robots using MATLAB and Simulink. And also We have solutions for the mobile robots with MATLAB, and for each tools which I have mentioned, there is a product page where it comes with the documentation, relevant examples, and so on. And for the platform design, mainly I was talking about the Simscape multibody. So there is a free on-ramps course available in MathWorks website for for helping you to get started with the Simscape multibody. You need to just have a MathWorks account for accessing the same.